Next talk is by Omer Tamuz. It will be about learning and repeated interactions on networks. And so, yeah.
Can you hear me? Does the microphone work?
Yes.
Make a test if you can hear my chewing the almond. No? Let the stragglers this is joint with Wan Ning, or you might know her as Kate Wang, who's sitting right over here. Please feel free to ask questions, interrupt, chat. And Philip Stock, who's at Yale. We're at Caltech. All right, so we're going to talk about learning on social networks. So people learn things by interacting with others. And one example you might have in mind is lifestyle choice, like what to eat. Do I want to put butter or margarine on my bread, or do I want my baby to sleep on their stomach on their back? The best practices of this change over time. And we're going to think about a setting where you observe what your friends do. And so you have to make repeated choices every day. You have to decide what you're going to eat, and you observe what your friends do. And your choices are going to influence what your friends do because they observe you. Now, because what I do influences my friends and what my friends do influences me, things get very complicated. So it's going to be in general impossible to write down an exact equation for the path that these things take. Things are going to depend on higher order beliefs, what I think about what you think. I did something, you saw me do it, now you do something. I have to think, oh, maybe you did this because you're influenced by me. So these are very hard inferences. So in general, these things are not so easy to try to understand exactly. What we're going to do is here's a preview of what the model is. We're going to have people who constantly get information. So every day I'm going to just be handed a little piece of information that tells me something about this, whether butter or margarine is better to eat. We're going to have a social network, so I observe some other people. I'm going to every day observe them and act myself. This is going to be in a completely rational framework. So we're going to have Bayesian agents. We're going to be playing an equilibrium of a Bayesian game, trying to maximize their utility. And the question is, how well is information aggregated in this process? Okay, so let me be more specific. We have a binary state of the world, which is either going to be, we'll call it G or B for good or bad. It's fixed once in the beginning of time, and let's just say that it's half good or bad. We're going to have a finite set of agents. We're going to have discrete time. We're going to have a social network. So N sub I will be all the agents that agent I can observe. We're going to imagine that the network is strongly connected. So I guess for the computer scientists, this is a well-known definition, but maybe for some others. But what it means is that there's the path of indirect observation from each person to each person. So maybe I don't observe Grant directly, but I observe Kate, who observes Grant. And this holds for any pair of players. We're going to have private signal distribution. So in each period in time, each player is going to get a private signal. And these signals are going to come from one of two possible distributions, mu G or mu B. The resolution here is not so great, or is this just is this a little hard to read? Or no? Yeah, okay. So this is a standard setting. You can imagine that maybe my signal is also 0 or 1, and when the state is good, there's slightly higher probability of getting a high signal. If the state is bad, there's slightly higher probability of getting a low signal, but this is more general. You get signals from some finite set, and the distribution depends somehow on the state. Okay, what's going to happen in every period? Each agent gets to observe everything that their friends did in the past, right? So HTI is the history that agent I observes, which includes all the actions of all our neighbors. And then this agent is going to receive one of these private signals that come from these two, one of these two distributions, depending on the state. Then this agent is going to choose an action, either put margarine on their bread or butter. You're going to get a payoff that's equal to 1 if the action that you chose matches the state, and 0. Otherwise, this is your stage payoff. This is what you get on day t. And what you're interested in is maximizing the expected discounted utility. So this discounted sum of your stage payouts. Okay. So basically, every day we learn a little bit about what is better. We butter our bread or margarine our bread, and then we tell our friends on Facebook what we had for breakfast, and we see what they had for breakfast. So far, so good. This defines a game, and we're just going to look at what happens in a Nash equilibrium, which means I choose a strategy, and each person chooses a strategy, and given what everybody else does, what I do maximizes my expected discounted utility. Yep. Okay.
Your own payoff the day off, but you don't observe the payoff of your neighbors.
Okay, that's a good question. You don't observe your payoff. If you observe your payoff, you'd immediately know the state, right? So you don't observe your payoff, but you do observe a signal each period. You can think of this signal as a noisy version of your payoff. Okay, so you can imagine that your payoff is, if you eat butter and the state is butter, your payoff is 1. You don't observe that. You observe another random variable that's 1 with probability 60% and 0 with probability 0%. Okay. But notice that your actions don't influence the information that you get. So we're not going to have here a story of sort of strategic experimentation where I take some risky action because it gives me more information. It's just going to be about, I get this information no matter what, and I just choose whatever action or strategy more generally gives me the highest utility. Yeah.
You don't observe your payoff, but you receive it after you should action.
Well, it's like when you eat butter or margarine, you don't observe what it does to your heart. You only get your actual payoff, when you die of old age. So that's how you want to think about this, okay? Or, every week you decide on the weekend whether to go to the mosque or to the church, and you only receive your reward in the afterlife.
So just to clarify, there is just a single theta.
This is what is the single
Theta.
Yeah. So you want to think about this as some ground truth. Margarine is healthier than butter.
It's not changing with time.
It doesn't change with time, and it's the same thing for everybody. Okay. But if you want to observe your payoffs, you can think of these signals that you get in each period as a noisy version of your payoff. So that would be equivalent, mathematically equivalent model.
So in the long run, we all learn the state just based on our own signals.
You guessed the next slide. Yes, but you're absolutely right. Right. So we get these ID signals. Even if I didn't even look at anybody else, I would know the state. Okay. Let me see if that's actually the next slide. Maybe. Okay. So these are the signals that I get up to time t, and the history of what everybody else did. This is what I know at time t. I don't observe payoffs, only signals and neighbors' actions. But I can think of the private signals as payoff plus noise. And just like Moritz said, because we get these ID private signals again and again and again, each person is going to eventually learn the state. So this is not like your sequential learning model, the herding models where sometimes everybody learns the state, but it might take a long time. The question that we're going to ask is how fast do they learn the state? So imagine that each signal that I get is very noisy. It's only correct with probability 51%, and I get only, but there are a lot of people. So if each person on their own might learn very, very slowly, but if there's 1 million of us, if we put all these signals together, we'd all learn very, very quickly. So the question is, what's going to happen here? So we're going to ask how fast they learn, but when we say they, is everybody going to learn at the same speed? Maybe some people learn at a different speed than others. This might depend on the network. We'll see. Okay, so what do I mean by the speed of learning, how fast they learn? We're going to be interested in the probability that you get it right. Okay, and this probability is going to, okay, here we have the probability that you get it wrong. And this probability is going to go to 0 just because you learn. But to calculate this number exactly, given a network, even a very simple network, take a a triangle of three agents who can observe each other, understanding in equilibrium, calculating exactly on the 10th day, what is the probability that they get it right, this is completely hopeless. But we can say, we can have some asymptotic statement about what happens in the long run. So let's start with just a single agent. We don't have a network. I just have me. I get a signal each period. I have to make a decision each period. We can ask, what's the probability that I get it wrong at time t? And this is a classical, Bayesian hypothesis testing from the 50s or who knows when. And what the result says is that the probability that I get it wrong at time t behaves something like e to the minus some number r1 times t. And in fact, you can calculate this number r1. This is like an exercise in large deviations. Depending on the signal structure, right? If my signal is more informative, I'll learn faster. This r1 will be bigger. If my signal is less informative, I'll learn more slowly. Okay, so you could, so this, sorry?
There's nothing Bayesian at this point.
Well, you know, this is sort of Bayesian, right? You're looking at this probability that I match the state. So you need a prior about the state. And the agents, when they make the decisions, they do a Bayesian calculation. They start with a prior. They say the state is with probability half good, really half bad. I got this information. I'm going to calculate my posterior and I'll figure out what's the posterior probability that the state is good or bad. Well, but how would you choose your action? So if I get a, you know, if the signal matches the state with probability 51%, and I get a signal that says, okay, the state is eat butter. This is equal.
Each step I have to make.
Yes. At each time period, you have to take an action. So after I see one signal, in order, you know, if my prior was that butter is very, very unlikely to be the better option, then even if I get a weak signal in favor of butter, it's not going to make me take the butter action. Maybe B should stand for butter instead of that. Okay, so this is what happens with one agent. Now you can ask, okay, what happens if we have n agents, but they have public signals, or you know, they somehow all share their signals, which is not part of our model. But let's imagine for a second, we have 1 million people now, they all share their signals. But that's the same thing as just one person who gets 1 million signals in each period. Right now we all have the same information. I don't even care. I know what you guys are all going to do. We all have the same information. We're all going to do the same thing. So it's the same as speeding up time by a factor of n, right? So we're just going to learn n times as fast. So the probability of making a mistake is going to shrink exponentially again with a rate that's n times higher. So what I'm going to define as the speed of learning is whatever rate we have here. So I'm going to imagine that the probability of making a mistake has this form. I'm going to take the log and divide by t and take a minus, and that extracts the coefficient before the t. Okay, so this is the speed of learning is, I define it as r, which is the limit of the log of this probability. And you know, if the probability of choosing incorrectly is of the form e to the minus rt, then this r is exactly going to be this. Okay. And it turns out that looking at these asymptotic rates, the speed of learning is tractable, and you can actually say something, even though you cannot say anything precise about what happens in period 17 and 18 and 19. Okay, so that's really our main reason for looking at these things. Well, okay, they're tractable, but they're asymptotic. So this only tells you about what happens. You know, it doesn't tell you anything about what happens in any particular period. This is something about the tail of the series of my probabilities of mistakes. So that's the downside of it. It has no welfare implications. But you know, it's like the central limit theorem doesn't tell you anything about what happens when you take a sum of 7 random variables. It tells you, you know, at the limit so and so happens, and you sort of keep your fingers crossed that it already happens for 5
So that there would be more, because then asymptotic, even the asymptotic rate would have welfare implications because you're getting more and more precise over time. There are more and more people. So some motion.
Well, there's the matter of sort of the order of limits of taking time to infinity, right? So if as you added more people, it would only kick in later and later in time, you might still not have a buffer. Okay, now the other thing to notice is whatever happens in our, remember we have n people, and when I'm on my own, when I don't observe anybody else, this is my rate of learning. When I observe everybody's private information, this is how quickly I learn. So what's going to happen in whatever model we choose and whatever network we choose is that the real rate has to be between this R1 and n times R1. I learn at least as fast as I do on my own, and I learn at most as fast as I would if I had all the information. Yeah.
So is the optimal application model the same as having a complete network? Or?
Yeah. That's part of the question you're being asked. That's a great question. Now we're saying, okay, imagine that we all saw each other. Every day we took this action. Would somehow seeing other people's action give me the same information as seeing their private signals? In fact, we have a previous paper that only looks at the complete network. This is sort of an extension or an elaboration on that paper. And you'll see the answer. What's the question?
Just wondering, following up on Ben's question, I think it was, if you took the patience parameter, if you made them very patient, and now you're going to take a stance on a double limit, could you speak to welfare then?
I also think not.
Because your lower results are for fixed patients.
We've thought a little bit about this, but let's maybe talk about it. I think it's still good.
What about, let me try one more time. What about some limit in the signal structure as the precision gets worse and worse so that
What I'm saying is every time you make a change, it could be that the time scale needed for this limit to actually kick in gets larger and larger. So you're never going to know anything about what happens at time 17. So more it says, okay, I don't care about time 17 because I'm more and more patient, but it could be that this thing grows, the time at which you convert to this limit grows even faster than you're, all right. Good, just a quick related literature. This is related to Victor-Ndani, Hirschheimer, and Welsh, and Banerjee. These are these by now classical papers on herd behavior. They have a lot of citations. This might be an exaggeration, but they have a lot of citations. It's a big industry. And in fact, we'll see that in the end, our conclusion is not going to be very different from there. So I'll get back to these papers. There's a bunch of papers, including by people in this room, who do similar exercises, but not in a quite rational model. For example, de Groot, Balai and Goyal, so these are all sorts of variants of some, quasi-Bayesian or quasi-rational or heuristic agents. But they do have social networks and signals and states and so on. We have some previous papers where we did something very similar, but we only got one signal in the beginning of time. And then we ask the same question of, of this literature, whether we learn at all or not. Now we're talking about something different. Everybody learns. The question is how quickly do we learn? And then we have another old paper where we again do something similar, but for the complete network. So this is your question, where everybody sees everybody. Here we also assume that agents are myopic, so they completely discount the future and just do whatever they think is best right now, not thinking ahead. Here we've also extended things to work for strategic agents who discount the future and play an equilibrium of this game. Okay, so here's the results. I'm going to fix my pair of conditional distribution. So this fixes the signal structure. Okay, so for example, again, imagine that the signals take values in 0 and 1, and when the state is good, it's slightly higher probability of being 1 than 0 and vice versa. And I'm going to define this number m, which is the highest log likelihood ratio that I get over my entire set of possible signal realizations, okay, multiplied by 2. So this sort of says, when I see a signal, what's the most it can convince me, either in the direction of good or in the direction of bad. So this is some measure of how strong the signals are. And remember, I get a signal from this, either this or this, depending on the state, every period. Here's the theorem. We're going to fix the signal distribution. Now you can take any equilibrium and any social network, of any size, take any discount factor. The speed of learning is at most m. So, yeah.
Something basic I don't recall. Do agents know the network or
Yes.
not?
It's sort of baked into the equilibrium assumption, right? So when I best respond, I calculate my expected utility. I need to know the network to understand, given everybody's strategies, what is going to be my utility. So agents know the network. You can imagine doing this in a state, in a some kind of random network where you don't know the network and you only see some information about it. And I think it should still work, but we haven't done that. More questions? Okay, so what does this tell us? It tells us you can add more and more agents. You can make it a large, complete network. You can make it, a two-dimensional grid and make it larger and larger and larger. But the speed of learning is never going to go above some constant. Let me give you a numerical example. We're going to have symmetric binary signals. And so the signals are also going to take value in G and B. And the probability that the signal is equal to the state is 0.9, right? So I get somebody tells me the state is G or the state is B, and they're correct with probability 0.9, and I get this again and again in every period. It turns out that a single agent learning speed is about 0.5, right? So the probability that I get it wrong behaves like e to the minus 0.5 times t. This m, so the strongest possible signal that I can get, which is both of them, is about 4.5. So what does that mean? 4.5 is an upper bound to the speed of learning, no matter what the network is. For example, 10 agents with public signals. So if we aggregated perfectly the information of 10 agents, we would have learning speed that's bigger than 4.5. But even 1 million agents that just observe the actions of their neighbors don't learn as fast as just these 10 agents who share their actual data. Yeah. Yeah.
Get information at this rate that depends on the path, and yet you
correlated information, right? So you're going to see 1 million actions in each period, but these actions are by people who also observe the same information as everybody else's actions in the previous periods. So these are not independent pieces of information. It's more or less the same information coming from these.
if they choose the same action.
Well, in equilibrium, they might, this is what this basically shows, that in equilibrium, there's going to be a lot of correlation here. People are going to have to choose an action that's not going to be very informative. And it kind of makes sense that they choose the same action, because if my signal is very weak and I see what 1 million people did, I'm just going to go sort of by the majority of what everybody's doing, and so is everybody else. So this is sort of what's going on. Of course, this works also on networks where everybody has degree 4 or 3 or whatever you want to choose. And there it's a bit, but you'll see why this holds more generally. Yes.
So after the first round, they could learn really, really well.
Yeah.
But the size of the network isn't changing. So asymptotically, eventually it's not going to be so hot. That's
right. So, this asymptotic rate tells you how quickly it converges to 0, not how it started in the beginning. Now, if you're talking about a complete network, then it makes sense that already in the first period, when I observe 1 million people, I get a very strong signal. But if you're talking about a 2-dimensional grid where everybody has 4 neighbors, when you grow the network, you don't get better signals in the beginning, right? So there you have a lot of people, and I don't know exactly what happens in the first periods, but it's conceivable that you never learn a lot. You just converge very slowly. Matt?
I think about a directed tree where there's loops. So, these are going to be taking actions that are just dependent on their own signals. And I would learn.
Good. Okay. So we're talking about strongly connected networks.
So you rule out these.
Yeah. So you could ask what happened. Let's talk about a particular tree where I just have one person who observes 1 million others and they observe nobody. Yeah. Then now I'm getting 1 million independent signals in each period, and I learn very, very quickly. What we do prove is that there's always going to be at least one person who learns this slowly, who learns as slow and M. In your case, it's the leaves of this tree. So what you do is you take the network and you decompose it into its strongly connected components. This gives you an undirected graph. It's going to have leaves somewhere. These leaves now don't get any information. They're a connected component that doesn't get any information from the outside, And there we can just apply this analysis and get very slow learning on that. More questions or thoughts? Or yeah.
Learn very fast.
Good. So I think that's a good question. I don't know, even on an infinite, let's say two-dimensional grid or tree or whatever, I don't know what to say about that. So this.
But if I have sort of degree 10 and then each of my kids has degree 10 as well, it would seem like I'm learning from, it's independent sources of information that I'm learning from.
You're saying a directed tree, or?
I guess so, yeah.
Yeah, then you learn very fast. On an undirected tree, if it's finite, then this theorem kicks in and we learn slowly. But it's about the asymptotic. So it could be that as the tree gets larger and larger, the time in which our learning becomes slow becomes later. And I don't know what would happen on an infinite tree. That's a good question. Good. So is this example? Yeah.
Gives you an even time first.
Not that I don't know how to say anything about any particular graph that would be better. Okay, how much time do I? Yeah, you in the back.
Is this found better than your complete network found?
Good. It's worse than our complete network bound. So I guess that's one answer to your question. Thank you, Kate. For the complete network, we have a better bound. And that better bound, in fact, it's sort of infinitely better because it works even for unbounded signals. The bound is the KL divergence between the signals, which here is going to be finite, but in general could be finite even if the signals are unbounded. And I actually think that should also be provable here, but it was already tricky to do this, and somebody else. Okay, so let's talk for a second about myopic and strategic behavior. So, but how much time do I have? 15. Okay, so there's a game here. There's some strategy. What's the strategic aspect? In the end, if I eat butter or margarine, it only affects my health. I don't care about your health. My utility is just my own health. So what's there to be strategic about here? Okay, but there is a strategic aspect to this. The thing is that I gain information from the actions of others, and my action influence other people's actions. So maybe by doing certain things, I can make you do something that will reveal to me more of the information that you have. So what you could imagine is that maybe I'm sort of indifferent between butter and margarine, but I think butter is better. And I see you doing butter. What I might do the next period is do margarine, even though I think it's slightly worse, to see what kind of reaction that gets from you. If you stick with butter, then I know, oh, okay, she has a really strong butter signal here. But if you also switch over to margarine, then I learn something about you not having very strong information either. So you could imagine that in equilibrium people play these sort of games. I think that would be an interesting paper to analyze this sort of strategic behavior. That's not what we do. What we do is we show that in the long run, you stop playing these games and you just act myopically and do the silly thing of saying, if my posterior belief that butter is better is higher than 50%, I eat butter, otherwise I eat margarine. Why is that? This LIT is my log likelihood ratio. It's my belief that the state is good, given the information I know, divided by my belief that the state is bad, given the information I know. And the myopically optimal action, so if I didn't care about the future, what would I do today? Well, if this was bigger than 0, which is the same as my posterior being bigger than half, I would play G, and if this was less than 0, I would play B. So I'm going to define this M as the myopically optimal action for an agent who has the same information that I have. In this game, people in general might not take the myopic action for exactly the reasons that I explained before. Right, so there might be a strategic reason not to choose MI. So here's two lemmas. The first lemma with two parts. In the first one says, in equilibrium, if at some point in time my log likelihood ratio is bigger than this constant that just depends on delta, on the discount factor, then the action that I take is the same as the myopic action. Why is that? The thing is, if I assign probability 99% to butter being good, and if I'm not very patient, then the hit that I get in my utility for playing margarine today is not worth everything that I'll gain in the future in expectation from these mind games. Okay. The next thing is there exists some random time t so that in equilibrium, everybody just, this happens. Everybody just starts behaving myopically from some point on. Why is that? Well, because we learn, we all get these signals and eventually our belief is going to converge to the truth. So at some point it's going to pass this threshold and we're going to stop behaving myopically. Okay. So that's the end of almost the end of the strategic part. We can just think about agents doing the myopically optimal thing. Yeah. I don't think so. So Kate, maybe, I mean, Kate constructed some example in a sort of closely related game. Oh, I see. Is playing myopic, that's a different. Okay, I think that there are equilibria where you don't play myopically, but I also think that you could find an example of a network where playing myopically is not going to be an equilibrium, where you're better off doing something strategic to try to get some. I don't have proof of that, but I think it's interesting. I don't know that people have studied much these sort of things. I don't know what to call them, but you know, playing mind games with information like this and trying to get a rise out of you to see how good your information is. I don't think, I think that if you're patient, you're not going to. Good. So here's a lemma, and it tells us that all agents learn at the same rate. So the first part says that if agent I can observe agent J, then the rate of agent I is going to be higher than of agent J, which immediately implies that all agents learn at the same rate because the network is strongly connected, right? So if I observe you, I learn at least at your rate, but then there's an indirect path from you back to me, and you learn, you know, higher along this path, and again, you learn more quickly.
Why is one true? Can you give any intuition?
Yeah, so I have a slide of it. So the intuition is what I think Ben called the imitation principle. So here's the imitation principle. Let's talk about myopic agents. So again, myopic agents are those that always take it. Oh, there he is. Ben, did you coin this term, the imitation principle? We were just wondering. No, who did?
Evan, I think.
Evan, I see. Okay, so Ben and Evan coined it in their joint paper. Good. So for myopic agents, what happens? I do the best thing that I can. Now, if I observe Alex, one of the things that I can do is to do what he did in the last period. But I'm doing something that's, you know, weakly better than this. I'm trying to maximize the probability of doing the right thing. I can just imitate him. That's one thing that's open to me. What I do gives me even higher probability of being right, which tells us that the probability that I'm wrong at time t is less than the probability that Alex, who I'm observing, was wrong at time t minus 1. Now, if you take the logs and the limits, you immediately get, for myopic agents, that the rate of this person is higher than the rate of this person, right? Because the difference between t and t minus 1 goes away when you divide by t and take the limit. But we don't have myopic agents, we have strategic agents. And for strategic agents, even though I can observe what Alex did, I might not want to do something that maximizes my expectation for that period. I might do something else. But what we have is an imitation principle for strategic agents, which means that the probability that I get it wrong cannot be more than some factor times the probability that Alex, sorry for picking on you so much, got it wrong. And it's sort of for the same reason that I talked about before. There's a limit to how patient I can be. And eventually, if he has a very, very high probability of being right, I'm not going to want to give that up. And I will imitate him or do better. So what happens is, if I observe Christian, once Christian's probability of getting it right or getting it wrong is very, very low, my probability of getting it right is also going to be very, very low, up to some constant. But now when we take logs and divide by t, take the limit to infinity, the constant is going to disappear.
But you only use this strategic thing in one direction. Didn't take into account that maybe I'm strategic too, and therefore it's not so clear you want to limit.
Well, it's because I observe what you did, I have the option of imitating you. I don't have to. And I mean, I understand that you're strategic, which means that maybe you're not doing the right thing, but I always have the option of imitating you. When I imitate you, I get it right with the same probability that you got it right. If you get it wrong with very, very low probability, I'm not going to give up this option of getting it wrong with that low probability. So I mean, somehow this is related to the fact that at the limit, people act myopically. Because I'm going to act myopically at the limit, you get this imitation principle again up to. Let me maybe continue, unless this is completely unclear. We can get back to it. And I mean, this idea of the imitation principle maybe goes back to Smith and Sorensen and the appeared in other places.
I think Beal and Karif coined the term, and then Evan and Sat and Lobo popularized.
Okay, thank you. Okay, so now that we have these initial things out of the way, let me tell you, why is it that our rate of learning is bounded? And no matter how many people we have, we will never learn more than, say, 10 people in the example that we had. So this is just a restatement of the theorem. Let's suppose towards a contradiction that the learning rate is actually strictly bigger than m. I learn faster than this bound. Let's imagine that the state is G. So because everybody learns, I know that everybody eventually is going to take the correct action. And
the speed of learning is per person, right? So there should be a
well, but we had a claim here because of this imitation principle.
right.
Everybody learns at the same rate. Okay. Good. Now we know that the rate of learning is r, which means that the probability that that person J doesn't take the correct action is about e to the minus RT. Now, when somebody observes J, when I say Nicole is this person J, she gets it wrong with probability e to the minus RT. So just me observing her, if I forget about everything and just look at her, this already gives me a very strong signal, right? This one bit of what she did in the last period gives me a very strong signal. The log likelihood ratio, just from observing her, right? This is the posterior belief in the good state condition for somebody who just gets to observe what she did in the previous period, divided by the bad state. The log likelihood ratio is about RT. So I get this very, very strong signal from looking at her. Now, I also have my private signals, and I got T of them because we're at time T. Each one of them, the strongest it could be is M. So all of these private signals put together, the log likelihood ratio is between minus MT and MT. So the strongest possible signal that, if I got a positive signal from her, the log likelihood ratio is RT. For me to do the other thing, my private signal needs to be less than minus RT. So that put together, my belief is less than a half. Does that make sense? This is impossible because each signal that I get has strength at most M. So when I put T of these together, the log likelihood ratio just sums up. These are conditionally independent signals. The sum of these signals cannot be that strong. So, maybe if you're not used to thinking about log likelihood ratios, but basically, here's what happens. If the probability that we all get it wrong decreases very, very fast, then the social information that we get becomes much stronger than our own private signals. Doesn't matter, even if all my private signals told me bad, 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 the fact that everybody's doing good trumps that. So then I don't even look at my private signals anymore, I just do what everybody else does. This is exactly the same mechanism from Bikhchandani, Hirschleifer, and Wells, where social learning stopped because people stop looking at their own private signals.
And much bigger than n. right, for this, because it could be like e to the power minus mt plus n, right? Minus mt minus
the degree, the degree of the.
right, the degree, right? So like t really has to be large. Like
Yes, it could be, as n grows, t might have to also grow.
yeah,
Exactly. So that's one of the disadvantages of this asymptotic. Exactly. It would be very nice. So for, this is why I don't know how to say anything but the infinite, say, two-dimensional grid.
yeah, because of that term, the size of the network.
Exactly. So it'd be really nice to get something, some kind of uniform convergence, or understand that it doesn't happen. That would also be interesting. But I always honestly don't know what the answer should be. Another thing that I don't know how to do is prove any lower bounds. So I know that when we're in a group, even in a complete graph, we learn at least as quickly as one person on their own. But I don't know how to prove that we learn any faster than one person. I know that we learn as fast as we do on our own because I have my information. I'm going to learn that quickly. But do I get asymptotically? Do I get any information for the rest of the people? I don't know how to do that. So that's a nice open problem if you want to think about something.
Or in a complete graph, but I can always take the first action of all of my neighbors and then all my signals, right? Because the very first signal they're going to act on. And then I ignore everyone else and just continue using my own signals.
But then your rate is going to be the same thing.
All right, again, for t large enough, it's going to be the same. Yeah, sure.
So again, the rate here is.
Yeah.
Yes, it's the same mechanism. If the social information is very strong, it swamps out the private signals. But if people stop looking at the private signals, then we're not learning anymore. And it can't be that the probability that we're getting it right goes to 1. That's basically it. So we have social learning in a rational setting on any network, strategic agents, they act repeatedly. And here, okay, I'm trying to advertise a little bit because this in general is hard to analyze. But if we look at the speed of learning, we get some tractability. We're able to say something. And specifically, we're able to say that this rate of learning is bounded from above. So no matter how many people you have, there's some limit to how quickly you can learn. That's it. Am I out of time or? Yeah.
Okay.
Questions, please?
So you're looking at the model where there is a large number of interactions with a small number of people who interact. But you take t to infinity. What the other extreme? Like a large number of people I interact with, but maybe I interact with them a small number of times. Is there anything you can like? That's different type of.
So you want each person to interact with a lot of people, but a few number of times with each person.
Yeah.
So the total number of interactions is still big. It's not like a fixed network where you'd have some other model. You're walking around the street and just talking to strangers.
Yeah, like open my Facebook, like I see a bunch of random,
When I open my Twitter, all I see is Ben. Right. So yeah, right. So you could imagine some kind of random matching model. You just get paired with somebody at random. That sounds very similar to what Gustavo Manso here does with Daryl Duffy. They have these models. Now they sort of take it to a limit of continuum and random matchings, and they see how beliefs evolve. So people have thought about them.
So if you don't have the strongly connected assumption, would you get some bound on the? So if you have sort of different rates for different agents, you still get something with this sort of analysis.
Okay, so let me just give you. Do we have a marker here? So imagine that I have one person who can observe many people. And these people cannot observe anybody. So the person at the middle is going to get a lot of information. This person is going to get these 5 independent signals in each period. So in fact, if you have n people like this, n minus 1 people around and one person in the middle, the rate of learning of the person in the middle is going to grow linearly with n. Right? The thing is, you're always going to have at least one person in the network, in this case, all of the leaves, for which this rate is going, this bound is going to apply.
Yeah, so your paper doesn't actually need a strongly connected graph. Because what you're saying is that in any graph, even if it's not strongly connected, there's components that will.
So we have that result in the paper. It's sort of a corollary of what happens in each connected component. There's an interesting question, which I think we can answer. Here, this person observes a lot of people, but what if you had a one directional chain like this? So this person observes nobody, and each person here just observes the person in front of them. There, it's not in the paper, but we're working there. I think, again, we're going to have a bound on the rate of learning. No matter how long this thing is, nobody's going to learn very quickly. This could apply to more general networks. So there's a lot of questions here about what can be said for particular graphs.
Okay, some logistics about what's going to happen next.